So, good evening. Let us solve the 43rd problem. Let us solve the 43rd, where two long parallel wires are along z direction at x is equal to 0 and x is equal to d. Okay, that means the distance between the two is d. The magnetic field along the x-axis has been plotted as shown in figure. Okay, this is a figure. Okay. The coordinates of point R is x is minus d. Okay. So we have to find what are the coordinates of point P. Okay. Here, the two things you have to remember. Okay, you have to identify two things. One is at R, the field is 0. The field is 0. Note that point. That's the first point. At R, the field, that means field due to the current I1 and field due to current I2 is equal and opposite. Let us write an equation for that. Mu naught I1 by 2 pi d is equal and opposite to mu naught I2 by 2 pi 2d. The distance of point R from the second conductor is 2d. So this gives the current I2 is 2 times the current I1. The current I2 is 2 times I1. It's a very important point. Next, at point P, field is minimum. The field is minimum. This is the second point. Okay. This is a good problem. Okay. So from graphic analysis, we can find at P point is field is minimum. Then let us write the formula for magnetic field at point P. So B is equal to mu naught I1 by 2 pi x plus mu naught I2 by 2 pi d minus x along negative y direction. Okay. Simplify this. Okay. So since field is minimum, the first derivative dB by dx is equal to 0. So differentiate this expression for B and differentiate with respect to x and equate to 0. So I will get minus 1 by x square plus 2 by d minus x whole square, okay, is equal to 0. You differentiate this. So once you simplify this, you will get x as d by root 2 plus 1. Okay, this is the answer. D by root 2 plus 1. So here the important point, first one is at R is field is 0. From that we'll get relation between I1 and I2. Then the right expression for B at a point P with respect to x, and differentiate with respect to x, equate to 0, which is the condition for minima. From that you will get x is equal to d by root 2 plus 1. So the answer is 1. Okay, good. This is a good question. Let us go to the next one. This is also the very, very important question. Okay. The next question is, a straight wire of length L, radius A, has current I. A particle of mass M and charge Q approaches the wire, moving with a velocity v in a direction anti-parallel to current. Okay. The line of motion of the particle is at a distance r from the axis of the wire. So here you have to assume that R is small compared to A, that is radius of the wire, so that magnetic field as seen by the particle is similar to that of long wire. Similar to that of long wire means the magnetic field B is equal to mu naught I by 2 pi R. Okay. Neglect the effects of end effects and assuming that the speed of the particle is so high, it crosses the wire quickly. That means impulse concept you had applied. It crosses the wire quickly means very short interval of time. Okay. Any short interval of time, you apply the force, we call that as impulse. We call that as impulse. Okay. And suffers a small deflection theta. We have to find the value of theta. You have to find the value of theta. Okay. So let me take my diagram. Okay. Okay, 1 minute. Yeah. So look at the diagram. So here we know that the force experienced by a charge F is equal to BQ sin theta. Sin theta is 1, BQV. Then we know that B is equal to mu naught I by 2 pi R. Okay. So this is the force experience. We know that force into time, small interval of time, is called change in impulse. Change in momentum, which is nothing but impulse. Change in momentum, which is nothing but impulse. So force into small interval of time, that is impulse. So substitute that. Okay. So this velocity into time will give the L. Okay. So from that you will get change in momentum. Okay. So we know that from that theta is equal to arc length by the radius concept. If you use theta is equal to delta P by P. So delta P by P is equal to theta. Okay. So but P is equal to MV and substitute, you will get theta value. So that's the answer. It's a good problem. It's also a good problem. Finding the deflection of the charged particle, which is moving anti-parallel to almost infinite long conductor for short interval of time. Okay. So look at the 45%. 45%. In 45%, a long straight cylindrical region of radius A carries a current along its length. The current density varies from the axis to the edge of cylinder according to the relation J is equal to J naught into 1 minus R by A, where R is the distance from the axis, which is lies between 0 and A, R value. So you have to find the value of magnetic field maximum when R is equal. That means you have to find the value of R where the magnetic field is maximum. Where the magnetic field is maximum. Okay. So just note down this one. So let us take this. Look at this one. So here Of course, you know how to find the current. Okay. So the current density J is equal to di by dA. Current density J is equal to di by A. Di is equal to J into dA, which already you know. So integrate on both sides, you will get total current. So if I apply that concept, current at distance R, look at this formula. Current this one. So 2 pi R dr is the current element. Okay, 2 pi R dr is the current element. Okay. Sorry, area element. 2 pi R dr is the area element. Multiply by the current density. J naught into 1 minus R by A will get current element. So if you integrate this element, you will get total current. Okay, total current up to R. So integrate that, you will get current flowing through a cross section of radius small r. This is the formula. Then apply the Ampere's law. Apply the Ampere's law. If you apply the Ampere's law, integral of B dot dl is equal to mu naught I, and substitute, you will get B is a function of R. B is function of R. Since he's asking maximum, differentiate with respect to R, you will get the field is maximum when R is equal to 3A by 4. Field is maximum at R is equal to 3A by 4. Okay, right. So there is one more problem similar to this. There's one more problem similar to this. Look at this one. This is the one. 49th problem. 49. So, an infinitely long hollow conducting cylinder of inner radius is R by 2. Outer radius is R. Carries a uniform current density along its length. Uniform current density along. So you have to find how the magnetic field varies with radial distance R from the axis. So this problem is based on Ampere's law. Ampere's law, which says the line integral of B dot dl is equal to mu naught times current. Mu naught times current. So if you apply this one, okay, but you have to take the limits. Current starts only from R is small r is equal to R by 2 to R small r is equal to R only. It's a hollow conducting cylinder. So let me explain this. Yeah. Look at this one. See here, first take case 1. Case 1. When x is equal to R by 2, less than R by 2, since no current is enclosed, B is 0. B is 0 according to Boyd's law. According to Ampere's law. According to Ampere's law. Next, take case 2. That is, x lies between R by 2 to R. And apply Ampere's law. Integral of B dot dl is equal to mu naught I. And B into 2 pi x is equal to mu naught times current density into area. Current density into area. Okay. So from that, you will get B value as a function of x. As a function of x. Okay. That is where x lies between R by 2 to R. The curve. Okay. Next, in case 3, when X is very much, when X is greater than R, completely the total current is enclosed. You can apply integral of B dot L is mu naught I. B into 2 pi X is mu naught. The total current enclosed will get B value, which is proportional to, inversely proportional to X. Okay. So your graph should reflect these three things. One, this is case 1, case 2, case 3. So let us go back to the graph. So I think the answer is the fourth one, because up to R by the answer is 4. Okay. So these are some of the typical questions. Okay. So if you have any other doubts, you can post in WhatsApp group. So I'll solve the remaining problems. We'll send if you have any doubts. So thank you.